In all regression problems, you have seen that we make certain assumptions on the error, and most of these assumptions are like the Gauss-Markov conditions. Then you have conditions that the error must be independent of x, rank of x must be equal to p, which is the number of variables involved. As long as estimation is concerned, we do not need to make any formal distributional assumption about the errors. However, when you go for other inferential problems like hypothesis testing, like confidence intervals, we need to have some distributional assumptions about the errors. And the most common distribution that we assume is that the errors are normally distributed, generally with 0 mean, and variance maybe sigma square, maybe sigma I square, depending on whether you have heteroscedasticity or homoscedasticity. The problem is, are we sure that the u's are normally distributed? So, we need to check whether the underlying error distribution is normal before we can actually apply the test that we do, usually the t-test or the f-test. So, they are all valid only if you have normality. So, what we will do in this module is to see how we can check for normality of the errors in a regression model. Let us look at the regression model y is equal to x beta plus u. Y as usual is the n component vector of responses, x is the n by p matrix of explanatory variables, there are p explanatory variables, and beta is the p dimensional vector of parameters. U of course is the error. We assume that expectation of u is 0 and dispersion of u is sigma square I n. This is all we need to assume as long as we are estimating the parameter beta. We can apply the least square method and get the estimates, and under these conditions we can show that beta hat would be a best linear unbiased estimator. But suppose we want to make other types of inferences. For instance, we want to check if some of the betas are equal to 0, etc. In that case, we need to assume some distributional form for u. In general, we assume that u is normally distributed with mean 0 and variance sigma square I n. The question is this assumption plausible? How do you know actually that u is what we are assuming it to be? So, there are several ways of checking this, primarily through the normal probability plot or the QQ plot. You can also have tests like the Shapiro-Wilks test and the Anderson-Darling test. So, what we will be doing here is to see what type of plots that we can have and see what type of tests that we can have. We will be discussing one type of plot, that is a normal probability plot, and we will discuss the Shapiro-Wilks test. The other tests or the other plots are similar, so we will just be looking at this too. Now, of course, you can always have a quick check. You can look at the histogram and see if it is bell shaped, more or less symmetric, which would be an indicator that it is normal. It will not exactly tell you it is normal, but it will tell you whether it is not normal if you have a very skewed histogram. Or you can also look at the proportion of observations within x bar plus minus 3s, s being the standard deviation, and you know that almost 99%, more than 99% in fact, of the observation should be within this interval. So, these are some of the quick checks that you can have, but we need to have more formal checks. So, our problem is to check if a sample x1, x2, xn comes from a normal mu sigma square population or not. For the time being, we will just look at x1, x2, xn and not at the errors as such. So, we will be discussing this in more generality, any sample whether it comes from the normal distribution or not, and then we will see how we can apply this to our problem of checking for the error distribution. Now, let u1, u2, un be a sample from the rectangular 0 1 distribution. Then the rth order statistics ur has PDF, f of ur is n factorial by r minus 1 factorial n minus r factorial into ur to the power of r minus 1 minus ur to the power of n minus r. This is straight from the usual results we have for order statistics. And now if we calculate the expectation of ur, it comes out to be r by n plus 1. The variance of ur comes out to be 1 by n plus 2 into r by n plus 1 into 1 minus r by n plus 1. And you can see that the variance goes to 0 as n becomes large. Now, let z1, z2, zn be IID normal 0 1. These are standard normal variables. We write u is equal to phi z. You know that the distribution function has the rectangular distribution. So, u equal to phi z would be rectangular 0 1. Now, let us make this correspondence. Say we have ur and we correspond this to the rth ordered value of z, that is zr. So, ur is equal to phi zr. In that case, if we invert this function phi, we can write zr is equal to phi inverse ur. And then expanding around the expected value of ur, which remember is r by n plus 1, we have zr is equal to phi inverse r by n plus 1 plus ur minus r by n plus 1 into the first derivative of phi inverse taken at the point r by n plus 1 plus ur minus r by n plus 1 square second derivative of phi inverse taken again at the point r by n plus 1 and so on so forth. And then if we take the expectation of zr now, we have the first term coming out as phi inverse r by n plus 1. There is no variable involved here, so this comes out as a constant. As for the second term, the expectation of ur would be r by n plus 1 and hence the second term would be 0. And the third term would give us the variance, but we have seen that the variance actually goes to 0 as n becomes large. So, we can approximate this and hence we can write expectation of zr is equal to phi inverse r by n plus 1 plus terms which go to 0. Let us denote by gamma r the expected value of zr. So, we have gamma r approximately phi r by n plus 1. There are other ways by which we can sometimes use a better approximation, where we take gamma r is equal to phi inverse r minus 3/8 by n plus 1/4. But we will not go into the derivation of those. Let us keep things simple. So, gamma r is approximately phi of r by n plus 1. Now, if x1, x2, xn are identically and independently distributed as normal mu sigma square, then by our previous result we have expectation of xr minus mu by sigma equal to gamma r, which means that we can write expectation of xr as mu plus sigma gamma r. So, xr can be approximated by mu plus sigma gamma r. It will not be exact because we have been taking expectations, but if you take the actual value and if the actual value is close to the expected value, then you would be expecting that it becomes a linear function of gamma r. So, what we do is we plot xr against gamma r. Mind you, gamma r can be obtained because it is expectation of zr and we know that it is phi r by n plus 1. So, given r we can always calculate this value and xr is from the sample. So, we plot this xr against the corresponding gamma r, and by what we have seen that it should come out as a linear function. It should be a straight line, and if it is a straight line, then we can say that the xi's are normal mu sigma square. This is what the normal probability plot gives us, a plot of gamma r against xr, and if the plot shows a straight line, then we can say that the underlying distribution is normal. How do you use this for the regression problem? In the regression problem, we had made the assumption that EYs are normal 0 sigma square identically and independently. The problem with checking for the normality of the EYs is that, remember, these EYs are unknown to us. In the model y is equal to x beta plus u, only y and x are known, beta are the parameters which are unknown, and the amount of contamination or error that is there in the model, that too is unknown. So, EYs would be unknown or unobservable. So, what we need to do is, we need to use a surrogate for the EYs. The usual estimates of the EYs would be the residuals, EIs. EIs are y minus or yi minus xi prime beta hat. So, EYs are yi minus xi prime beta and EIs are yi minus xi prime beta hat. So, if beta hat is close to beta, then the EIs would be close to the EYs. And we also know that these EIs are also normally distributed if EYs are normal, and it has a mean 0 and the variance sigma square into 1 minus HII. This HII are the diagonal of the hat matrix. Hat matrix, remember, is the matrix x into x prime x inverse into x prime, which actually HII are the leverages that you use when you are searching for outliers. So, EI actually is normal, therefore, we define TI to be EI by root over 1 minus HII, and you can multiply this by SI if you want, which is the variance, and you get the normal distribution. So, if you do not divide by S, you have a normal distribution with mean 0 and variance sigma square. If you divide by sigma, you have a standard normal distribution, but then the sigma needs to be estimated by the sample standard deviation. And then you plot the ordered value of the TIs against gamma r, and if this comes out as a straight line, then you can say that the EIs and hence the EYs are normal. Of course, EYs are unobservable, as I said at the very beginning. So, what we can say is that we can assume it to be normal because it is representative in this sense that it is estimated by the EIs are normal. So, this would be a normal probability check for the error variance or error distribution to be normal or not. A more formal test is the Shapiro-Wilks test. There are alternative tests to this, and in fact, very often the Kolmogorov-Smirnov test can also be used. But let us just look at the Shapiro-Wilks test. So, we have Z1, Z2, Zn, which are the order statistics from a normal 0, 1 population. This is a sample from this population, and let MR be the expected value of ZR and VRS be the covariance between ZR and ZS, that is the Rth and the Sth ordered statistics. Now, let x1, x2, xn be a set of any ordered observations. So, this is a new set of observations that we given, and what we want to do is we want to test the null hypothesis that this x1, x2, xn is a sample from a normal mu sigma square population. Now, under the null hypothesis, XR is equal to mu plus sigma ZR, because XR minus mu by sigma under the null hypothesis would be standard normal. So, that will be equal to ZR, and hence we can write this XR is equal to mu plus sigma ZR, or the expected value of XR is equal to mu plus sigma MR, MR being the expected value of ZR. Now, we model this as, this is a true value, mind you. So, generally how we model y as expected value of y plus some error. So, in this case we are modeling XR as its expected value, which is mu plus sigma MR plus some error epsilon r. What would be the expected value of epsilon r? It is going to be 0. What would be the covariance between epsilon r and epsilon s? It will be the same as the covariance for XR, and XR's coefficient will be the same as the coefficient the covariance of ZR into sigma square, because XR is mu plus sigma ZR. So, the covariance of epsilon r epsilon s is sigma square VRS. Now let us construct this matrix capital V, which is composed of elements VRS. So it's V11, V12, etc. up to V1n, and then the last row would be Vn1 up to Vnn. Now if we apply GLS to this model to estimate mu and sigma, we would be minimizing a delta function here. Before I come to delta, just look at how we construct the vectors here. So let x vector denote x1, x2, xn. The m vector denote m1, m2, mr, and we have already got v. So what we want to minimize now would be x minus mu 1 vector minus sigma m vector prime b inverse x minus mu 1 minus sigma m. The derivative of delta with respect to mu and equate it to 0, we get the equation mu 1 prime v inverse 1 is equal to x prime v inverse 1 minus sigma m prime v inverse 1. Similarly, taking the derivative of delta with respect to sigma, we have sigma m prime v inverse m is equal to x prime v inverse m minus mu times 1 prime v inverse m. Now, on solving these two equations and then using some of the properties of a symmetric distribution, symmetric distributions, you have the order statistics on either side of the symmetry, they have the same ordinates, etc. So, if we use those, we have mu hat turns out to be equal to x bar, and sigma hat turns out to be m prime b inverse x by m prime b inverse m. Now, what we do is we define S as the sample covariance. So, basically it is 1 by n summation I equal to 1 to n xi minus x bar squared. It is primarily the sample variance in this case, and this will be an unbiased estimator of sigma square. So, if you write r square is equal to m prime v inverse m and c square is equal to m prime v inverse m, then we define the Shapiro-Wilks statistics as W equal to r to the power of 4 sigma hat square by c square s square. So, sigma hat, mind you, sigma hat square comes from what we have done assuming normality, and s square is the raw sample variance, and if we have made a good assumption, then this should be close enough. So, we can write W in terms of slightly differently as a prime x square by s square. This is the usual standard form that it is written in, and I will explain why it is written in this fashion, where A is m prime v inverse by m prime v inverse m to the power of half. Now, if you write W in this case, W, if it is too small, then we will say that this is the hypothesis is rejected. That means that if you have a very small value of W, the assumption of normality is rejected. As I said, the W should be close to 1 in the sense that the ratio should be close to 1, and you have the other constants involved also. So, if you have a very small value, you cannot say that the underlying distribution is normal. Now, Shapiro and Wilks actually tabulated this critical points W alpha. They also tabulated this A values. So, they wrote it in terms of the A, so that you can see that ultimately you write W just in terms of A, X and S. S is from the sample, X is the ordered observations, and A is something that you get from the tabulated value of the Shapiro-Wilks. So, if you need a formal test, you can use this test and check for the normality assumption. In our case, what will happen? In our case, of course, we will be looking at the EIs. So, again as before, as we did for the normal probability plot, our x's would be the EIs. So, you have the EIs and then you check whether this is going to be normal 0 sigma square 1 minus HII, and you can use the Shapiro-Wilks test on the residuals for this check. In a regression setup, the normality assumption is required when we do go for confidence intervals or for hypothesis testing. What we had been discussing in this module is how do we check for normality. We did a general discussion in the sense that if you are given a sample of size n, say, how do you know that this sample comes from a normal population? A very quick check would be to use the normal probability plot, and of course you have the other plots like the quantile plots. That would give us a very good idea. But then these are not a very formal way of doing it, because what one person conceives as a straight line, another person may say it's not a straight line. Okay? So, because the points obviously would not lie on a straight line exactly. So, we can also go for a formal test. There are several such tests. The Kolmogorov-Smirnov test would work. The Anderson-Darling test is there. But what we did today was to look at the Shapiro-Wilks test. And we saw how we can use the Shapiro-Wilks test to check for the normality of the errors of a regression model.